Okay, 2.4, rates in real life. We want to think about different ways we can interpret the derivative. So in general, the derivative, f prime of x, is always going to indicate some sort of rate of change of a function at x. All right, so if the units for x are years and the units for f of x are people, then if we set up df dx, this is the derivative of f with respect to x, what we have is a change in the number of people compared to the number of years. All right, or the rate of change in population. Now, graphically, we could think of this as being the slope of the tangent line to the graph. All right, in that case, what we're doing is we're also making a comparison, right, a rate of change, how quickly the y values are changing compared to how quickly the x values are changing. Delta y over delta x can mean the same thing as the change in y over the change in x, which is how we sometimes represent slope. All right, next up, we could think of this in a physical environment. All right, we could have our position function. Sometimes this is going to be a height function. Say we shoot a rocket up into the air, exactly what's the height of the rocket, that sort of idea. Typically, we're going to represent this with s of t is the most common way to represent our position function. But if we take the derivative of that and find s prime of t, the derivative of s, all right, in Leibniz notation, that would be ds dt. So taking the derivative of the position function and comparing it to time, we call that velocity, v of t. So ds dt is a change in the height compared to the change in time. All right, finally, we could go ahead and take the derivative of our velocity function and find v prime of t. In Leibniz notation, that's dv dt. That's how quickly the velocity is changing with respect to time. We call that acceleration. All right, and it's kind of important to get down, especially in physics applications, exactly how these connect together. That our position, its derivative is going to be velocity. The derivative of velocity is always going to be acceleration. All right, in our course, we also get business context for this. All right, whenever we hear that keyword marginal cost or marginal revenue or marginal profit, we'll talk about this later, but what we're really saying when we're talking about marginal is the marginal cost would be approximately the additional cost for making exactly one more item. All right, so it's going to be a comparison, but for all of our intents and purposes, what we can do is we can think whenever you hear marginal, this word marginal is going to be a rate of change, or what you're going to be thinking is marginal automatically for all of our applications means derivative. All right, so we don't have to go any further than that, really. Marginal, whenever you hear this big keyword, you always want to be thinking derivative for all of our contexts throughout this entire class. All right, so I hope this helps out. Remember, it's always a rate of change for every single one of these applications. Derivative means rate of change. Hope this helps.